Okay, good afternoon. You should have picked up a handout here. Handout, are we on? Yes. Should have picked up a handout here. What this handout is a revision to the first part of chapter 16, which is about potential, the concept of electric potential. It's also posted online, so if you lose yours, there's a PDF copy online, but it tends to be much more convenient to have a paper copy. It's a revision to chapter 16, and the way it's different is that it starts right in with the things we're going to use the most. The current chapter 16 starts in a sort of abstract way and doesn't cut to the chase until a little bit later, and we're starting here with some things that I think are just a little easier to understand than the things we're going to use the most. Up until now, we've been talking mostly about electric field and electric force. Force changes momentum, so we're basically talking about the momentum principle, aka Newton's second law. And now what we're going to do is start talking about energy, introduce energy concepts and the energy principle in, again, a slightly more abstract way, just as we've been doing with electric field. So the big topic for this chapter is the topic of electric potential. And just as electric field has units of force per unit charge, force per coulomb, so newtons per coulomb, and it's the field, the force that there would be if there were a charge there to feel it. Electric potential is actually analogous to that. Instead of potential energy, it's potential energy per coulomb, or the potential energy that a system would have if you put a particle there with some charge. So that's the basic idea, and we're going to introduce it today and work on this concept for the next week or so, and then we'll continue to use it throughout the course. A quick review of some ideas about energy, just to, because we probably haven't thought about it a lot over the summer, and maybe a slightly different take. If you have a single particle, and a particle in the physics sense, this little point thing that doesn't have any internal structure, so it can't get hot, can't vibrate or flop or rotate or anything like that, so kind of like an electron. The energy of a particle really only has two parts. It can have kinetic energy, which is energy due to its motion, and it has rest energy, mc squared, the energy associated with having its mass. And that's it. It can't have vibrational energy or rotational energy. A single particle doesn't have any potential energy because potential energy is due to interactions of more than one thing. So that's it. That's all a particle can have. And approximately the kinetic energy of a particle can be written to half mv squared, and that's probably a very familiar formula to you. You've certainly used this before. It's actually approximate because this is valid only when the speed of the particle is actually a lot less than the speed of light. And so when you get up to the speed of, near the speed of light, this actually isn't true. This is not the kinetic energy of a particle. And then we actually have to go for the complete, relativistically correct formula for the particle energy, which is mc squared over the square root of 1 minus v squared over c squared. This is the magnitude of the velocity. And the kinetic energy of the particle then is actually equal to this whole thing minus mc squared. And we won't very often be dealing with particles that are going very close to the speed of light. And so we won't very often need to worry about this. Occasionally, though, if we talk about particles and particle accelerators that can get up to something like 0.999 times the speed of light, then we actually are going to have to do it this way, which is sort of annoying. But most of the time, this approximation is good. And believe it or not, This actually does come from this if you grind through and do enough algebra, and you probably don't want to do that. But if you're bored someday, you can do that. So most of the time, we're going to be in a regime where this is a perfectly good approximation, and we're going to use that. So we'll be approximate for the moment. And since the only kind of energy a particle can have is its rest energy, and we're going to consider situations where the particle isn't changing identity, nothing's turning, we're not undergoing fusion or fission or reacting positrons and electrons, then we actually have the energy principle for a single particle is just the change in kinetic energy is the external work done on the particle. So if you take a system of a particle, a proton, and you throw it, it gains kinetic energy depending on how much work you did on it in throwing it. So you take a baseball, that's your particle. You throw it, it's gained kinetic energy equal to the work you did on it, that kind of thing. And it can't get hot because it doesn't have any internal degrees of freedom. So that's it. And that's not really all that interesting. And remember, let me remind you that what delta means in this case. The symbol delta always means final minus initial in these situations where we've got a change. So implicit in talking about changes in energy is we are always identifying a system that has some initial state, something happens in between, there's some final state, and the energy changed due to inputs, outputs, or rearranging, and that's what we're talking about. So whenever we have a delta K, that's a final minus initial, and it's due to something that went on in between. Okay? Now that's sort of boring and not very interesting, but when you get to a system that has more than one particle in it, two interacting particles or more, then you can actually get some other interesting things happen. So if we have two or more particles, then the kinetic energy of the system can change for a variety of reasons. The kinetic energy of the system, the change in kinetic energy of the system could be due to some work done by forces external to the system, but also could be done due to forces internal to the system. For example, if you took a system consisting of a proton and an electron, you said, that's my system, both particles, and you let them go, they exert forces on each other. They make fields at each other's location. They exert forces on each other. They speed up. These forces do work on the particles. But those are forces internal to the system. So those are internal forces. So we have to consider the work done by internal forces. That can change the energy. An external force would be, for example, the gravitational force, since we just took the proton and the electron as our system. The gravitational force would be an external force. And during the time that these guys are coming closer together and speeding up, the gravitational force probably did a little work on them. So they probably gained a teeny amount of speed in the y direction, but actually not very much, because the electric forces are typically so much stronger than the gravitational forces that these things happen so quickly, the gravitational force just doesn't have much time to act. And in a complicated system, there can also be energy transferred into the system thermally. This is called energy transferred thermally. And all that really means is there's a temperature difference between the system and its surroundings. So if you put, your system includes some metal plates, and your metal plates are touching a really hot object, then energy flows from the hot object into the metal plates. That's a thermal transfer of energy, and the plates get hot. So that's a possibility too. Now, in most of the systems we're talking about, things happen quickly and they're kind of isolated. So in general, that's not going to be a big deal for us. But we put it in to be complete at the moment. So this is due to a temperature difference. Now, this equation has some terms that have to do with things happening inside the system and some terms that have to do with things external to the system. And we'd actually like to rearrange it so that we have on one side all the internal terms, and on the other side all the terms due to external interactions. And so what we want to do is take this term and move it onto the other side. So that's all we're going to do. And so we get the change in kinetic energy of a system plus a negative of the work done by internal forces is equal to the work done by external forces plus any thermal transfer of energy into the system. Okay, I just did algebra, right? And now here's we get a definition. We take this quantity, the negative of the work done by internal forces. So if we have the proton and the electron, they're exerting forces on each other. The particles are being displaced. So those forces are doing work and the particles are speeding up. And we call that the negative of the work done by internal forces. We call that the change in the potential energy of the system. So U is potential energy of the system, and we say that anything that happens, all the work done by internal forces, we're just going to call a change of potential energy of a system. So if we had a mass and a spring, for example, and we say they're both our system, we hold on to the spring, we pull on the mass, and stretch the spring. The spring is exerting a force on the mass and doing some work, but that's inside the system. So we say we've increased the potential energy by stretching the spring. So that's another example of an internal work, potential energy. And so we write this equation as the change in kinetic energy of the system plus the change in potential energy of the system is equal to external work done plus thermal transfer of energy into the system. And this is the energy principle for a multi-particle system. So that's actually worth remembering. So let's just look at an example. What would this actually mean? Okay, so let's take a simple system, or a system that's simple to think about. Let's consider a capacitor, which we discovered last week has the very nice property that the field inside the capacitor is essentially uniform. And so it doesn't change with location, and so that actually makes the math really easy. So that's very convenient. So we have this electric field in here that's uniform due to these charged plates. And we're going to need an initial and a final situation. So we'll call this location A, and we'll call that location B. And what we're going to do is we're going to take a proton. So proton. And so the proton is it's a location A and it's at rest. Zero kinetic energy, right? So it's at rest at location A. I'm going to put it here, we're just going to let go of it. Okay, so I put this proton at location A, and I let go of it, and what's going to happen? Okay, is there a force on the proton? Yeah. Okay, and so it's going to move toward B, picking up speed, picking up speed, picking up speed. And when it gets to B, we're going to say that's our final situation. And B is just before it crashes into the other plate. So we can say our final situation is any time we want. We don't have to wait till it crashes into the plate. So the final proton at B, kinetic energy is not zero. So that's our initial and final situation. And we want to explore what this energy equation means. So let's write it up here again. The change in kinetic energy of the system plus the change in potential energy of the system is equal to the external work plus the energy transferred thermally into the system for the system. And to make the system an interesting system, we're going to take everything as our system. So our system is going to include the proton and the charged plates in the field and the inside. And usually when we talk about potential energy, we'll be talking about systems like this, where it includes some particle or particles and the particles that make a field that's affecting them. So that's what we're going to end up doing here. Okay, so let's think about what's going to happen between our initial and our final states here. Of course, this equation isn't, we can amplify this equation a little bit for this system, because there are actually two pieces to the system. There's the proton and there are the plates, right? So we actually want to say here, we're going to expand it out and we'll say the change in energy of the proton, kinetic energy of the proton, plus the change of kinetic energy of the plates, plus the change of potential energy of the system is external work plus energy transferred into the system thermally. So now let's think about what terms in this equation we can get rid of because they're not very important. They're near zero or nearly zero. We're going to say that this process takes place in a capacitor that's not touching anything hot or cold, so it's isolated from its surroundings. Or else it's already in equilibrium with its surroundings. It's sitting here and it's already at room temperature. So this is in fact just zero because it's not gaining or losing energy by being in contact with something at a different temperature. All right, now let's see. There's a gravitational force acting. That's certainly an external force, right? Because our system is the proton and the plates. The gravitational force doesn't do much work on the plates because they're just sitting there on a support, so they don't actually move down. So the work done by that on the plates is zero. And in fact, even though this proton is moving and the gravitational force, there is indeed a gravitational force acting on it. It is so small compared to the electric force that it doesn't have a chance to do very much work on this proton. And so the work done by the gravitational force on the proton is so nearly zero compared to everything else going on that we're going to say that that's approximately zero, very close to zero. And now since we've got zero on this side for external inputs, this better add up to zero on this side, right? Or we're in deep trouble. Okay, so let's think about forces. There's certainly electric force on the proton. You guys told me it was going to be in that direction, and it's equal to plus E times the electric field, right? And that's an internal force, and that's probably going to actually do some work. So there's going to be a force on the plates too. Does the kinetic energy of the plates change very much, though? Not a lot, right? Practically negligible. So that does almost no work, and so that's about zero. So we're down to two terms that are going to have to change. Now, what was the sign of the kinetic energy change of the proton? We started it here at rest, and by the time it got over here, it was moving. So was this term positive, negative, or zero? Positive. Okay, so that's a positive term. This better come out negative then, right? Or else we're in deep trouble. So the potential energy of the system between the proton here and the proton here should have gone down. Since the kinetic energy went up, the potential energy went down. We stretched the electric spring and we were holding this proton here when it didn't want to be here. So there's potential energy, and then we let go, and spontaneously it gains kinetic energy, and the potential energy of the system should be going down. Let's see how we calculate that. So, okay, so this is the negative of the internal work, And the internal work is the work done by this electric force. So remember that work is that in general, use a darker marker. Remember that work is the sum of the force acting in the x direction times the x displacement plus the force acting in the y direction times the y displacement plus the force acting in the z direction times the z displacement. That's the work in some process. And we picked this process so that nothing's happening in y and z at the moment, just to simplify our lives, so we can only look at x here. So we get that, let's see, there's a force, the displacement, we'll call this just delta x. So we have a delta x here. And this force, the x component, was a plus e times e sub x. So this is the internal work. But we want the negative of that, so we have to take a negative of that. And that should give us the change in electric potential energy of the system for this situation. So let's see if this comes out to be a negative quantity. Okay, we better look at the signs of all these things. Okay, plus E, that's positive, that's good. E sub x, is the x component of the electric field in this case positive or negative? Positive, it's pointing that way, so that's good. Delta x is x final minus x initial. Okay, so is delta x positive or negative going from A to B? That's positive. Okay, all those are positive. We have this minus sign, so this thing does come out to be negative, and that's good. So the kinetic energy increases, the potential energy goes down for this proton here. Okay? Questions? Okay, let's do it for, yes?
Yeah, I got a quick one. We're saying that potential is equal to the negative internal work.
Yep, change in potential energy. Negative the internal work, yes.
And the change in potential is negative. Would that not make the internal work positive just fine?
It was. The internal work was positive because this is the internal work. This is the force, and that's the displacement. So Kevin's question is, if this quantity is negative, doesn't that mean the internal work had to have been positive? And it was. This force plus EEX acted through a positive distance EX. This force was in the direction of displacement, so it did positive work on this proton, speeding it up. So the internal work was positive. The negative of that is negative. Remember, the negative sign came from switching sides of the equation. Yeah, so the message here is that signs are extraordinarily important here. And if you drop a minus sign, you're going to have the world going backwards. You're going to have protons moving the wrong direction, and you're going to have negative kinetic energies, and you're going to have all sorts of horrible contradictions that you don't want. So you actually have to think physically about signs here. Okay, let's do it for an electron. So we have an electron. We have an electron at A, at rest. Gonna move it to B. Now this is kind of a different situation, isn't it? If I release an electron here at rest, is it going to go to B? No, it isn't, is it? It's going to go that way and hit that plate. So if I need to get it to B, what do I have to do? I got to apply a force on it, don't I? So I have to attach a string to it and pull it along to get there. So we actually need some sort of an external force here. We need a force by my hand, grabbing this electron and pulling it along. And if I'm going to pull it along at constant speed, how big does that force need to be? Actually, at constant speed, it only needs to be equal to that force, right? Because with the net forces, so here's the electric force. And it only needs to be equal to that force. Now, I agree that actually to get it moving, for a brief instant, I've got to exert a force that's just slightly larger just to get it going. But then at that point, Newton's second law says that the particle should continue at a constant velocity if there's zero net force on it. So once we get it moving, all I have to do is apply a force that's equal and opposite to the electric force, and it moves over here at constant speed. And then there's a very brief moment, if I want it to be at rest, that I'm going to have to push back just a little to slow it down. But those are very small. So, and we almost never talk about those parts of the process, which actually do have to happen. Okay. So final is the electron at B, still at rest. All right, so let's see here. We have the change in kinetic energy of the proton plus the change in kinetic energy of the plates. Oops, sorry, thank you. Electron. Plus delta U is external work plus energy transferred in thermally. Again, no thermal transfer of energy. Again, the plates aren't picking up any kinetic energy. What about the change in kinetic energy of the electron? Starts at rest. We move it at constant speed, then we bring it back to rest. Kinetic energy change is zero, isn't it? It's at rest at the beginning, it's at rest at the end. So that's actually a zero. And that must mean the change in potential energy of the system equals the external work. And what's your guess? Is this going to be a positive or a negative number? Have we stored up any energy in the system by moving the electron over there? We've moved the electron over here. Have we stored up any energy in here? What happens when I release it? It's going to go back that way, speeding up, isn't it? So it suddenly gains kinetic energy. So in fact, we must have put some potential energy into this. We must have increased the potential energy of the system so that when we release it, it can be converted into kinetic energy. Okay, so let's work it out. Let's see, we've got this. This is the work done by internal forces. So we have a minus internal work here. And so we have a minus E times a EX times a delta X. And so this number actually comes out to a plus E EX delta X. And that says the potential energy of the system has actually gone up. Delta U is positive. And that makes sense because we did positive work. We pulled the electron over in that direction, and we actually did positive work. So that sort of balances out. So now let's actually look at these situations. For a proton we came out with a delta U, which was equal to a minus E sub x delta x. And for an electron, we have a delta U, which is equal to a plus E sub x delta x. And what we want to do is what we did for electric field. We want to express this as the product of the charge times some quantity that's the same regardless of what charge might or might not be there. Okay, so actually let me move this line down. Delta U is plus EX delta X. Okay, now we have room to write here. So we want to write this as the product of the charge on the particle times some quantity. So what's the quantity? It's plus E times what? It's going to be a minus EX delta X. Here I want to write this as the product of the charge on the electron times some quantity. What's that quantity? Negative EX delta X. And so in both cases, the thing that's the same actually is this thing, that minus EX delta X thing. Yes, awesome. No, just stretching? Okay. And that's the thing that's called the change in electric potential. So we have delta V is minus, in general, EX delta X minus EY delta Y minus EZ delta Z. It's called the change in potential, not potential energy. And it's related to potential energy in the following way. We have a change in potential energy. In fact, that's a definition. Change in potential energy is just the charge of the particle times delta V. So we have a change. We have a difference in potential between these points, whether there's a particle there or not. And once we put a particle there and move it along that path, then the system changes potential energy, and we figure out by multiplying by the potential, by the charge of the particle. And now we'll do some examples to make it concrete. But this is called electric potential, and what are the units going to be? This has units of joules, right? So that's energy. This has units of coulombs. So this better be joules per coulomb. And it's so important that a joule per coulomb is in fact given its own unit. It's defined as a volt. And 1 volt is 1 joule per coulomb. This means, by the way, that since this has units of volts, and this displacement has units of meters, there's actually another unit for electric field. You can write it as newtons per coulomb, and what else could you write it as? If volts is going to be something times meters, volts per meter. So it actually turns out that 1 volt per meter is equal to 1 newton per coulomb, and they're equivalent quantities for electric field. Okay, you ready to do an example? Do an example with some numbers. Okay, we like this capacitor. We'll use this capacitor. Here's A, here's B. We've got an electric field in here that way. Let's say that I'll rewrite that in a minute. But let's say that location A is, let me use the numbers I've got here. We'll make it simple. We'll put the origin at A, 0, 0, 0 meters. And B, we'll say, is at 0.100 meters. Okay? And the electric field in this region is 300 newtons per coulomb or volts per meter. Now let's rewrite our definition of potential difference over here. Potential difference is a minus EX delta X plus EY delta Y plus EZ delta Z. And notice that implies a path. You have to pick a path between the initial and final locations. We'll show that it doesn't actually matter what path you pick, but you do have to pick one, otherwise you don't know how to compute this. But okay, so given this, let's find going from location A to location B. So A to B, let's compute the potential difference. Do this on your paper, and then we'll check it together. Okay? So we have a negative sign, and then we have E sub x is 300 newtons per coulomb or volts per meter. Maybe I should write it as volts per meter, so it's obvious the units come out right. Times, what's delta x? It's plus 0.1 meters, isn't it? So it's, and then EY and EZ are 0, and so there's just 0 times 0. So we get a negative 30 volts. So what you get? Okay. Okay, suppose we move a proton from A to B. What's the change in potential energy of the system? So we do what we did here. We release the proton at A. It moves to B. What's the change in potential energy of the system? Remember that delta U is Q delta V, where this Q, it has a sign, right? It can be a positive number or a negative number, and delta V can be a positive number or a negative number. Okay, so the potential energy change when you move a proton is E times delta V, which is a plus 1.6 times 10 to the minus 19 coulombs times 30 volts, which is what? But then there's, that was a negative though, wasn't it? So that's a negative 4.8 times 10 to the minus 18 joules, right? Is that what you got? So that makes sense because the potential energy of the system is going down because the kinetic energy is going up. So that makes sense. What about an electron? If we move an electron from here to here, what's the change in potential energy of the system? It's just the negative of that, isn't it? So it's going to be delta U is plus 4.8 times 10 to the minus 18 joules. Okay? So fairly simple. Okay, let's try a couple. Okay, so we've got an electric field that's uniform in this region. It points down. And the electric field is 0, negative 300, 0 newtons per coulomb. B is at, this is 220 and this is 200. So what you need to do is find the potential difference, delta V, along a path going from B to C. Well, it's either plus or minus 600 volts, and we're almost evenly divided, so let's work it out. So we want, okay, E sub x is 0 and E sub z is 0. So we want here, we have a delta v as a minus Ey delta y, right? So we have E sub y is negative 300. So we have a negative 300 volts per meter. And delta y, this is going from there to there, so it's final minus initial. So it's 0 here and 2 there. So delta y is a negative 2 meters. And that gives us, we've got 1, 2, 3 minus signs. So looks like negative 600 volts. So final and initial are really important, right? Because what if we'd said going from C to B? Then it would be positive 600 volts, wouldn't it? So final and initial really matter here. Okay, let's try another one. Okay, we have a uniform electric field in this region. B is at the origin, C is at negative 2, 0, 0, E is that. Okay, what's the potential difference going on a path from B to C? So we're going on a path from B to C. Oh, just about unanimous. Okay, the big vote is for plus 800 volts, so let's see here. We have a minus Ey delta y, so we have a minus 400 volts per meter times delta y is negative, right? So that's negative 2 meters, and so we get plus 800 volts, which is what most people got, right? So do you notice a pattern here? Actually, notice that when the path goes in the direction opposite to the electric field, the potential is going up. And in the previous one, when the path went in a direction the same as the electric field, the potential was actually going down. Okay, let's try one more. Now, this time, we've got an electric field that's not in the plus or minus y direction. It's negative 200, negative 300, 0 volts per meter. B is still at the origin, C is at negative 2, and we want to go along a path from B to C. Okay? Well, we mostly like negative 600 volts. Let's see. Here we have, in this case, we have a negative Ex delta x plus Ey delta y. But actually, delta x was 0 in this case, right? So that one comes out to 0. So we have a minus negative 300 times a negative 2, which comes out to a negative 600 volts, which is what you said. And I guess you lucked out. We don't have time for the last more complicated one, so we'll do that next time.